another method. And this other method is called top-down design. Top-down design was invented in the 1950s and 60s. And it was invented pretty well by NASA, and it was done to get the Apollo program working. The Apollo program, for those of you that don't remember or weren't born yet, was the moon landings. What happened was that old JF got up and he said, and we intend to send a man to the moon and bring him back before the end of the decade. Now that really, really worried all the Apollo scientists, because basically everything they'd lit up until that point had blown up. So they hadn't done very well. So he had just given them an impossible job to do. And they got a bit upset by that. So one of them said, hang on, there is a method, there is a way of doing the impossible. And he said, this is what we do. It's called top-down design. Firstly, you take the impossible. Then you can't do the impossible, but you break the impossible down into what it consists of. So you break the impossibles into horribly difficult. So now instead of one impossible task, we have 3 horribly difficult tasks. Now you look at each horribly difficult task and you break that down into tricky tasks. So now each horribly difficult task is 3 tricky tasks. Okay, that's looking better. Now we break each tricky task down into tasks. And then we give each task to a tradesman, and off he goes and does it. Once all the tasks have been completed, then we've completed the tricky tasks. Once we've completed all the tricky tasks, then we've completed all the horribly difficult tasks. And once we've completed all the horribly difficult tasks, we've completed the impossible. Now, this might seem pretty obvious to you as a way of doing things, but it's not the way it used to be done. In the past, what we used to do is we would do what was called bottom-up design, so that the man that designed things would design every single aspect. For instance, when the Titanic was designed and built, it was done by Jacob Adams, I think his name was, or Andrews. And Mr. Andrews designed every part of the Titanic, from the keel plate to the door handles. It was bottom-up design. That's the way it used to be done. One engineer who had godlike status would design everything, and he would be continuously redesigning things, so that he was actually on board the Titanic redesigning it while it was, well, hitting icebergs and sinking. Now, bottom-up design relied on the fact that you had this one engineer who was fantastic and godlike, and he designed everything and got it all right. Now, what this meant was that there was an awful lot of times that they got it wrong. For every bridge that these engineers built, there were probably 2 or 3 that fell down. Isengard Kingdom Brunel was a great engineer, but he also designed tunnels which filled up with water. He designed ships which were useless. So every time they designed something good, they quite often designed something which was rubbish. That was the problem with bottom-up design. It all depended on one person. Another example is the Spitfire. The designer of the Spitfire, he designed every part of that plane, and he knew that if he died, the Spitfire would die with him. Now, towards the end, he actually got cancer, and his doctor told him that he should rest. If he rested, he'd get another couple of years' life. But he knew that if he rested, the Spitfire wouldn't get built, so he carried on working. He designed the Spitfire, and he died early, which is a shame for him, but good for everybody else. So that was a problem. Everything was done by one engineer who designed it from top to bottom, in fact from bottom to top. Top-down design is a much better system. Top-down design, we break the problem into sub-problems, so that we say, okay, we need to build a spacecraft which is going to get to the moon and come back. So what we'll do is we'll break it into sub-problems. So, right, Team A, you'll be in charge of designing the rocket that's going to get you there. Team B, you'll be in charge of designing the life support systems. And Team C, you'll be in charge of designing the system that's going to take the men down to the moon and bring them back. Now it's got to be manageable jobs. So we'll take Team A, who are doing the rocket that's going to get there. What we'll do is we'll break that into Team A1. And Team A1 will work on the first stage rocket. Team A2 will work on the second stage. Team A3 will work on the third stage rocket. And then within Team A1, Team A1-1 will work on the rocket engine. Team A1-2 will work on the fuel tanks. Team A1-3 will work on the electronics. Now these are becoming manageable tasks. Each team is an independent team. Central tenets of top-down design is that there are flows. Problems, I'll just write that in there. Problems go down. Problems go from the top boss down to the bottom. So basically each person goes down and kicks the next person. So problems go down, solutions go up. So you don't go to your boss with a problem, you go to your boss with a solution. If you have a problem, you give it to the next person below you and get him to fix it. And if he turns around and he's the last person in the line, it's tough for him. So the first tenet of top-down design is that problems go down, solutions come up. The second important tenet of top-down design is that each team is isolated from every other team. There's no crossover. That team is isolated, this is isolated, this team is isolated, and within the teams, the tasks teams are isolated from each other. There's no interaction, and there's no micromanaging. The big boss at the top does not come along and go to one of the workers and say, how's it going, I want you to do this. That's not how it works. So each team is completely independent, and what they do must be completely independent from everybody else. It's a great system, top-down design, because it means that a job that would take 10 million man-hours, what we do is, we do it in 10 million man-hours, but we do it using 10,000 men. So we break the problem down into smaller problems and dole out the problems. And then we even construct things using top-down design. So that if you were to, if you need an aircraft carrier, you need an aircraft carrier in a hurry. In the olden days, they would build an aircraft carrier, they'd lay down the keel plate, and then they'd build an aircraft carrier on top of it. One rivet, one bolt at a time. Well, not quite one bolt, but they'd build it from the bottom and they'd build it up slowly, one bit at a time. Nowadays, that's not how we build things. Nowadays, an aircraft carrier is built in sections. Huge, great big sections. It's built in 3 different dockyards in sections. That way, it can be built in a third of the time. Then those sections are brought together, lifted up by giant cranes, and the sections are welded together. So nowadays, we're building things in pieces and assembling. It's the principle of top-down design. Rather than building everything in one linear fashion, we build it all at the same time and then just bolt it together at the end. So top-down design has allowed us to build things much quicker. It's quickened the rate of progress, so that if we discover oil off of the Northwest Shelf, we can have an oil rig built in 3 months and we can have it on site in 4. So the rate of technology has increased due to things like top-down design. However, sometimes it goes horribly, horribly wrong. Like it did with Apollo 13. With Apollo 13, there was a big explosion. And it was all wrong, and they said, yeah, Houston, we have a problem. And Houston said, we suggest you evacuate. If it had been me, I'd have said, I already have. It's in the bottom of my suit right now. Now, so they had a problem. They had to evacuate the service module, which is this thing here, the command module. They had to evacuate the command module and go into the lunar lander. Lunar lander. So they would use the lunar lander as a lifeboat. That was the plan. Now, the problem they had was they trucked across into the lunar lander and everything was all good. Everything was going well for a little while. And then they started getting high carbon dioxide levels. If you get too much carbon dioxide, you tend to do things like, pass out, fall asleep, die, that sort of thing. So that was considered a bad thing. Now, inside of the lunar lander, they had a machine which was designed to get rid of the carbon dioxide. The machine was called a carbon dioxide scrubber. And it had a carbon dioxide scrubber element inside there, and that's basically a big sponge with limestone on it. And the limestone would absorb the carbon dioxide. Their carbon dioxide scrubber element was kind of circular shaped. Now, Mission Control said, okay, your carbon dioxide scrubber is being used up, so you need to pop into the command module, grab the carbon dioxide scrubber out of there, and pop it into the lunar lander. No big deal. Except for the carbon dioxide scrubber in the lunar lander was kind of squarish shape. The reason this had happened is because of top-down design. Top-down design had said each team works completely independently from the other team. So the people building the command module went out and bought a scrubber. The people building the lunar lander went out and bought a scrubber. Top-down design said there was no need for anybody to talk to anybody else. So they all bought different scrubbers, and the thing didn't fit. Luckily, they managed to get it to fit. But that's an example of how top-down design can fail. Okay. The way we implement top-down design in software is by using what's called subroutines. Subroutines are small sub-programs. So with subroutines, what we do is we create these subroutines, and this is the summer subroutine. It's a sub-program. It's its own little bit of ladder. And a subroutine has got a little header at the top which says subroutine, just here, and it has a return. Now what the return does is the return makes sure that it always goes back to the right place. It always goes back to where it came from. Now, what that means is the program comes along and it says, is it summertime? If it is summertime, go off and do the summer subroutine. So go off and do the summer sub-program. And then when it's done that, it does a return, which brings it precisely back to this point. it will never go into an infinite loop because the return makes sure it goes back to the right point. Or it sees the summer switch here. Is it winter? If it's winter, go off and do the winter subroutine. And this is the winter subroutine. And once again, it starts with the word subroutine and ends with the word return. And because there's a return there, it will absolutely come back to the right place. So it will not create an infinite loop. So subroutines are small sub-programs. They're small programs that live all by themselves that do certain jobs. Now the nice thing about this type of program is, this is the main program. This is all that my main program consists of. Now in the event of, I come along 8 months later and I upload this from the PLC and I've got no comments, I now look at this program and I try and work out what it does with no comments. So I come along and I look at it and it says, alright, when input 1 is on, it goes off and does that thing. And when input 1 is off, it goes off and does that thing. Okay, so I now go off and I look up to see, I get my hardware, my wiring diagram out, and I go up and look up input 1. And I find that the input 1 is actually the summer switch. So, I now know that's the summer switch there, and that's the summer switch there. So, when the summer switch is on, go off and do that stuff, which I bet is the summer stuff. Makes sense? And when the summer switch is off, go off and do that stuff, which I bet is the winter stuff. Now, what's just happened is, I know what this program does. By looking up just one input, I've worked out what the program does. I don't know the details of how it does it, but I've got the gist of how the program works. When it's summertime, it goes off and does whatever is happening in that subroutine. When it's winter time, it goes off and does whatever happens in that subroutine. So without looking up every single thing, every single input, I've got the gist of how the program works. And I did it despite the fact that I didn't have any comments. So the nice thing about top-down design is the maintenance person coming along 18 months later can work out what's going on. Even nicer, if the maintenance if the problem he's got is that the reticulation has come on, he knows, well, the reticulation only comes on in the summer, so I only need look in the summer subroutine, which is a small little bit of code. It's only 4 lines. I know where it is because it's in the place labeled summer subroutine, so it's easy enough to find. And I then got a few things to look up in the summer subroutine, and lo and behold, there's a reticulation output. So it's much, much easier to do maintenance on. It's much, much easier to fault find. It takes a little bit longer to write the program initially because you've got to be thinking, okay, I'll make a summer subroutine and I'll make a winter subroutine, and so there's a little bit more typing in to do. But having typed it in, it's actually quicker to fault find. So the install person will actually be away sooner, because if he gets a fault in the summer, he only has a small thing he needs to look at. If he gets a fault in the winter, he only has a small section he needs to look at. So it's easier for the install bloke, and it's much easier for the maintenance people, because it cuts down the number of places they need to look. One thing that's very common with programming is to have alarms. Now normally the alarms are dotted all over your program. What you could do instead is have an alarm subroutine, so that in the main program there's just a jump to alarm subroutine. And then you put all of the alarms in the alarm subroutine. Then if you need to change an alarm value, you know precisely where it's going to be. It's going to be in the alarm subroutine. You don't need to grub through 400 lines of code to try and find the alarm that you're looking for. You just go to the alarm subroutine where there's maybe 15 alarms. It's a lot quicker. So here I have my summer subroutine, and here I have my winter subroutine. Small sub-programs, and my main program consists of jumps to my subroutine, or calls they're called. So my main program consists of nothing but calls to subroutines. There's some rules about subroutines. You must begin with subroutine and end with return. On ladder, because ladder's a piece of crap, every line on ladder must have an output. So if you've got subroutine on one line in ladder, so I've got subroutine there, I've also got to have some kind of output. Quite often you can use just a dummy output. One problem you have with subroutines is, if you've got two subroutines, say you've got a subroutine there which is the summer subroutine, and you've got a subroutine there which is the winter subroutine, and then your main program calls either this summer one or the winter one. If you turn something on in the summer subroutine, it may get stuck on, and it may not, and then you need to actively turn it off in the winter subroutine. To give you an example of how this could happen, let's have a look at this. I come along in my program and I look at my program and it says, is it summertime? Oh yes, it's summertime, it's nice and warm. I'll go off and do the summer subroutine. So now I jump off and do the summer subroutine and I say, okay, is the temperature high? Okay, I'll turn the cooling on. Is it late evening? No, it's not, I won't turn the lights on. Is it early morning? Oh yes, it is early morning. So because it is early morning, what I'm going to do is I'm going to turn my reticulation on. So my reticulation has just come on. And then the next thing I do is go return. And return jumps me back to the main program. It jumps me back to this point in the main program. And then it says, is it winter time? No, it's not. So I'll ignore that line and go back. Is it summertime? Yes, it is. I'll go off and do that summer stuff again. Now, if by pure mischance I just finished doing my summer subroutine and then suddenly it gets very, very cold. So instead of going off and doing it, I come along here and say, is it summer? Oh no, it's very cold. So it's now winter. So I jump off and do my winter subroutine now. Now in my winter subroutine, I'm going to check to see if the temperature's low and turn the heating on. I'm going to check to see if it's early evening and turn the lights on. The retic is still on because I turned it on in the summer. The retic is stuck on. My problem is, because I'm not checking the reticulation in the winter, then the reticulation will stay on forever. So what I need to have is I need to have a line in my winter subroutine which has an unlatch in it. Now I'd insert it just in there, and that line would look like an unlatch. An unlatch means press the stop button. So I need an unlatch in there for the retic. And what that means is go out and press the stop button on the retic. Now 99.99% of the time I won't need to do this because the stop button would have been pressed by the summer subroutine. But there's just a chance that I may have switched from summer to winter in the interval while the retic was still on. If that happens, the retic gets stuck on. So just in case that happens, I need an unlatch in my winter subroutine. And the unlatch means go off and press the stop button. So, if you turn anything, if something needs to be specifically switched off, you need to put an unlatch in that subroutine. in case it was switched on by the other subroutine. So, advantages and disadvantages. Advantage-wise, top-down design breaks the problem down. It allows us to do the impossible, which means that we don't get overwhelmed by really, really big jobs. It's easy to fault find because the problem's broken down into individual smaller problems, so we only need to look in one place. As an installer, after a while we end up with a whole library of small jobs, so that if we get called to another job where they say, oh yeah, we want you to do a summer subroutine and a winter subroutine, well, it's easy, I've already done that. So it's just a case of cut and paste and change the name on the top and charge them the full price. So I end up with a modular library, which soon enough means I don't have to write any programs ever again. I just cut and paste. It's also easy for the maintenance people to modify, because once again you only need to look in one place rather than grub through a whole great stack of ladder logic. Against it, it's not immediately instinctive. Our immediate instinctive way of programming is to do serial programming. Just jump in with both feet, start at the beginning and end at the end. Also, it is, as our trade thinking has always been, I'm going to do my job and bugger everybody else. So top-down design really involves looking at the entire problem. So it goes kind of against our trade thinking. Having said that, because it makes maintenance so much easier, we should always write our programs using top-down design. We should use subroutines to break the huge, great, massive lines and lines of ladder into lots of small chunks, which are easier to digest. So that's how we should do our programming. We should never use jumps. We should never use flowcharting. And we should try to avoid serial programming even for the simple programs.